of Research Organization for Nuclear Energy, Dr. Rohadi Awaludin, respectable Head of Research Center for Accelerator Technology, Dr. Muhammad Rifai, Honorable Speaker from Department of Particle and Nuclear Physics, KEK Sokendai, Japan, Professor Takanori Hara, Honorable Speaker from Department of Material Structure Science, KEK Sokendai, Japan, Professor Kazuhiro Mori, Research Organization for Nuclear Energy, Dr. Rohadi Awaludin, respectable Sokendai, Japan, Professor Naoto Yamamoto, Honorable Speaker from Dean School of High Energy Accelerator Science, KEK Sokendai, Japan, Professor Tohru Honda, and respectable all of participants of this seminar. Welcome to the Accelerator Talk Series 9, Capacity Building and Research Accelerator-Based in KEK Sokendai, Japan. My name is Karina, the Master of Ceremony of today's seminar. I'm very pleased to see you here and welcome all of you to this seminar. Today's seminar is collaboration from Research Center for Accelerator Technology National Research and Innovation Agency or BRIN with KEK Sokendai, Japan in capacity building and research collaboration. On behalf of the host, we assign of greatest appreciation to each and every one of you for being able to attend this seminar. It is such a great opportunity that we are gathering in virtual Zoom. We hope to have a fruitful discussion and insight. Ladies and gentlemen, before we start, please let me announce some notes for the participants. The first, please keep your microphone mute whenever other speakers are doing their presentation. The second, a question and discussion on the Q&A session can be placed in the Zoom chat during the speaker presentation and moderator will select the question, or you can use the raise hand feature and moderator will allow you to unmute your microphone and ask directly. Ladies and gentlemen, please allow me first the read of agenda today. The first agenda is the opening session, and then the second is seminar session led by moderator. Without further ado, we are now going to listen Chairman of Research Organization for Nuclear Energy, Dr. Rohadi Awaludin, to deliver his welcome remarks and officially open the seminar. Please welcome Mr. Rohadi.
Thank you. Good morning, ladies and gentlemen in Jakarta, and good afternoon, our colleagues from Japan. Assalamualaikum warahmatullahi wabarakatuh. First of all, I would like to welcome our distinguished speakers and guests today, Professor Takanori Hara, Professor Kazuhiro Mori, Professor Naoto Yamamoto, and Professor Tohru Honda. Thank you very much for your valuable time being with us today. And you will share your experience, your knowledge to our researchers here in Indonesia. And some of our guests today from KEK, Co-Energy Kenkyu. Actually, I was in several times. I visited KEK in 1998 to 1990 or 2000s. 3 over time I visited KEK in Tsukuba, and I have some experience in using such small angle neutron scatter, small angle X-ray scattering in the facility. It's very nice facility, I think. So thank you very much for your time today with us and sharing your experience in research and development using synchronous radiation and some other topics. And secondly, I would like to welcome all of participants today in this Accelerator talk. I think it's very important for us and very useful to increase our knowledge, our skill related to accelerator. And today we have a very great speakers, and I believe that it will be very useful to accelerate, to increase our knowledge in accelerator technology. And finally, I'd like to thank organizing committee, which has prepared this event very good, and hopefully we can continue this accelerator talk in the next series. And it will be, I believe, it will be very useful, very valuable for us, and increasing and accelerating our activity and accelerate. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Mr. Rohadi Awaludin, for the welcome remarks and open the seminar. Now we are going to the listen Head of Research Center for Accelerator Technology, Dr. Muhammad Rifai, to deliver his welcome remarks. Please welcome Mr. Rifai.
Okay, thank you, Mrs. Karina. So, Assalamualaikum warahmatullahi wabarakatuh. Thank you very much, the chairman of the research organization for the technology, nuclear energy, Dr. Rohadi Awaludin, for attending our seminar, and thank you very much for Sensei that belong to KEK, Honda Sensei, and Hara Sensei, Mori Sensei, and also Yamamoto Sensei that want to have a time for talk with us regarding about our Asato talk that we have discussed before when I came to KEK. So I hope with this kind of seminar, some our young researcher have new knowledge regarding about accelerators, and then KEK facility, also the application of the accelerator. So I hope they can pursue their master degree or doctor degree in the future to KEK or maybe Sokendai University in Japan. So with this kind of seminar, webinar, they can have we have a discussion fruitful with our young researcher and with Sensei in the KEK and also in Sokendai University. So thank you very much for your coming to our seminar. So I will be the moderator in this seminar, so I will talk with you soon. Thank you very much.
Thank you, Mr. Rifai, for the welcome remarks. Ladies and gentlemen, we are now moved to the main agenda, that is presentation and discussion from the keynote speech, which will be delivered by Professor Takanori Hara about research project in KEK, Reveal the Mysteries of the Universe. Professor Kazuhiro Mori about studies of battery materials using neutron scattering at GPAC MLF. Professor Naoto Yamamoto about studies for future light source at KEK-PF. Professor Tohru Honda about guide for study in Japan at KEK and Sokendai. The keynote speech will be moderated by Dr. Muhammad Rifai. Before we going to the presentation, I will read the curriculum vitae of our moderator, Dr. Muhammad Rifai. Is a head of Center for Accelerator Technology. The last education is PhD in Dosisa University. The research is about material science, metallurgy, metal and alloys, safer plastic deformation, material characterization, and mechanical testing. And then the last working experience are preliminary research collaboration with Kyushu University, joint research agreement with Dosisa University, principal investigator at Research and Innovation COVID-19 LPDP, principal investigator at Bulk Nanostructure Metal Consortium, and then the other is editorship of the journal. Ladies and gentlemen, let us welcome our moderator, Dr. Muhammad Rifai. Bapak Muhammad Rifai, now the time is yours.
Okay, thank you very much, Ms. Karina. So we will start our agenda today. There will be four presenter that have to be Hara Sensei, Mori Sensei, Yamamoto Sensei, and then the last one is Honda Sensei. So before we start our presentation today, so I would like to read CV for Hara Sensei. Maybe Karina can show the. Okay. So our first presenter will be Professor Takanori Hara, or Hara Sensei. He belong to the professor at the High Energy Accelerator Research Organization, KEK, and also Institute in Particle Nuclear Studies, IPNS. His education is PhD in physics at Osaka University, Osaka, Japan, and his current research is about high energy physics with the particle physics experiments. and work experience will be at associate professor at High Energy Accelerator Research Organization (KEK), and also Institute of Particle Nuclear Studies from 2009 until 2018, and then before that, he worked also in research associate in Osaka University from 1996 to 2008. And maybe after graduate from his PhD, he also have a fellowship from GSPS from 93 until 95. So, maybe we can start our first presenter, Mr. Francis. Maybe you can start your presentation. And you have 30 minutes. I will. Okay.
Yeah, but can you hear me well?
Yeah, we can hear you.
Okay, so is it okay to share my screen?
Yeah, please.
Okay. I hope you can see my slides now.
Yeah, we can see your slide.
Okay, so let me start my reports. Actually, so spending 30 minutes, I would like to introduce the project ongoing in the KEK IPNS, the Institute of Particle and Nuclear Studies. So first of all, thank you very much for making an opportunity for us to introduce the KEK projects here. So today's my talk title is the research project in KEK IPNS, because I belonging to the IPNS, the Particle and Nuclear Studies parts. And my subtitle is to reveal the mysteries of the universe. So using my 30 minutes time interval, so I would like to introduce the many projects, especially for the CP violation projects I will explain later in KEK, and also I would like to introduce other type of the experiments. Okay. First, I would like to inform you of the location of the KEK. Probably, so you know Japan, Tokyo area, but actually, so the KEK is located away from 6 kilometers away from the Tokyo, the capital in Japan. But this Tokyo is also roughly the 5,600 kilometers away from the BRIN in Indonesia. Then, so this is the location field of the KEK, the institute. As you can see, the KEK area is very rich in the nature. So you can see the big mountain here. There's so many fields are here. So inside the natures, we have the KEK Institute. So because my talk is concentrate on the accelerator physics, particle physics. So I just show the main accelerator ring in here, so-called the super KKB accelerator. The diameter is roughly 1 kilometer. So today I will introduce some projects using the super KKB accelerators mainly. Then I suppose you're the student in the scientific field, right? So then but anyway, so let me explain what is the elementary particles. So actually, so this is in my slide. Probably you can see there are some spots here, black spots here. But to just magnify these spots, it's a sort of the form of the insect. And the official name of this insect is Drosophila, as far as I checked in the English, Japanese dictionaries. So the sort of the insects, actually the size of this insect is 3 meters long, 3 millimeters long. Usually the top of the head of the insects, there are so many bacteria. The size of the bacteria is 0.5 micrometers. Of course, this kind of the bacteria is composed from the protein molecule. The size of the protein molecule is roughly 10 to the minus 8 meters. Then, so the protein molecule consists from the atoms. Actually, the size of the atom is the 1 atobon, 10 to the minus 10th meters. So then, so that these single atoms also consist from the nucleons. and also the electrons. And also that this nucleon comes from the composition of the proton and the neutrons. Actually, the size of the proton or neutron is corresponding to the 10 to the minus 15 meters or something. Then let's see the inside of this proton. So as you can see, there are three particles in here. There are two up-type quarks and one down-type quarks. So I hope you have heard about the quarks so far. But anyway, so that by dividing the material around the world, so that we can finally reach this kind of the very small particles, such like the electrons, such like the up quark or down quarks. Actually, the elementary particle is the smallest unit of matters as we know. So the elementary particle physics is a research to investigate what kind of physical laws these elementary particles obey. So that this is the, how to say, the sort of a big definition of the elementary particle physics. So far, we already found the 17 different types of the elementary particles. So the 6 quarks, up-type the quarks, down-type quark, and also the charm, strange, top, bottom. This is the sort of the nickname of the different type of the quarks. So in total, we already know the 6 type of quarks here. And also that we know the another 6 type of leptons. One is electron and muon, tau, and also the neutrinos corresponding to this, the electron, muon, tau. In total, 6 different type of leptons here. Plus, we know the full gauge particle. Gauge particle, it means the sort of the force intermediator particles. For example, the electroweak force. So the gamma is a sort of the force intermediator particles. Same as for the strong nuclear interaction. So the gluons, and also the weak interaction for Z and D, W and Z. In total, 4 different type of the gauge particle we already know. And plus, roughly the 10 years ago or something, so the Higgs particle, which gives the mass to the particle, we already found this, the Higgs particle. In total, 6 quarks, 6 leptons, and 4 gauge particles plus Higgs boson. This the 17 particles we already know. Actually, the particle physicists always seeking the ultimate theory. The ultimate theory is to answer the question, is it possible to describe the universe with a total of 17 particles? So that this is the sort of the ultimate questions, and also the, how to say, the main, the motivation of the particle physicist. Then another question is that why does investigating elementary particles unravel the universe? This is also related to my talk title. Probably as, let's see, the around your, how to say, the around you. So the in our universe, we have the Earth and also the so many galaxies. But probably you know the beginning of the universe, we call it a sort of the Big Bang, fireball universe. So on this the Big Bang, just looking back in time at the history of the universe. For example, the 3 minutes to 20 minutes after the birth of the universe, this is the age of the atomic nuclei. And the 10 to the minus 6 seconds to the 10 seconds after the birth of the universe, this was the era dominated by the hadrons and the leptons. And 10 to the minus 12 to 10 to the minus 6 seconds after the birth of the universe, this was the age of quarks. So the current, the universe, we can see the many celestial objects like Earth, Sun, etc., etc. However, at the early stage of the universe, it means the sort of the beginning of the universe, this is dominated by the quarks and leptons and elementary particles. So to understand the origin of the universe, so the important thing is the investigating the elementary particles behavior. Then, okay, so that this is just the schematic view of the Big Bang. Actually, Big Bang is the very pure energies. From these very pure energies that we believed matter and antimatter was created equally. However, next question is, so what these have in common? Actually, around you, you can see, or you can touch the desks or chairs, etc. Also, you live in the Earth, and Earth are belonging to some galaxy. Of course, the life force, for example, the amoeba is there are so many amoebas around us. Not only for this kind of the life force, for example, the drawings such like the Gioconda drawn by the Da Vinci. So this is also exist here, exist in our worlds. And also from the ancient age, this is the pyramids, those Sphinx. So do you know what these have in common? The answer is these things are matters. So let's go back to the history of the universe. Again, so that this is a schematic view of the evolution of the universe. Now we are here, the 13.8 billion years now from the beginning of the universe. But at the beginning of the universe, as I explained before, the matter and the antimatter were created equally. However, after the 13.8 billion years later, we just only see the matters. It means the antimatter was disappeared because of some reasons. So then there must be a difference in the way matter and antimatter behave. So, actually, so for the moment, we do not know why only the antimatter disappeared from the in the history of the universe. This is one of the big mystery of the universe now. Another big mystery is the dark matter. Probably you have already heard about it. We already know dark matter exists there because the most massive spiral galaxy spin faster than expected. Actually, the spinning speed of the celestial body inside the center of the galaxy and almost center of the galaxy, it is completely matched with the expectations or calculated the speed. However, the celestial bodies in the tail of the galaxy here, so the speed of the spinning speed is much faster than the expected value. So this schematic view, the line shows the calculated or expected the speed of the spinning. But on the other hand, the spinning speed is shown in this kind of the white lines. So it means something there, something invisible there around the galaxies to keep the speed of the spinning of these celestial bodies in the tail of the galaxies. Another evidence is the so-called the Einstein ring. Again, so here, the Earth, we are here. And also let's suppose there are some galaxy here. And between our Earth and the galaxy, if there's something invisible heavy object exists, this something heavy invisible object can bend the light of the galaxy. Then finally, so that we can see some image of the distorted image of the galaxies at Earth. This kind of the distorted galaxy image has been already observed in Earth, so many cases. So, however, from this kind of the evidence, we already know dark matter exists. However, we do not know what is dark matters. Actually, so there are so many candidates of the dark matters. For example, the complex materials or macroscopic celestial bodies. This is one of the, the candidates. And some people believe this kind of the dark matter is a sort of the classical field wave. And also between the classical field wave and also the macroscopic celestial bodies, Another candidate is the elementary particles. For example, the light particles or heavy particles, or sometimes we call it WIMPs. This is a weakly interacted massive particles and so on. So anyway, to understand the elementary particle physics, it may also be connected to the connected to the mystery of the dark matters. So apart from the dark matters and also the origin of the missing antimatters, there are so many other questions or mysteries in the universe. For example, the origin of mass, and also the origin of the heavy elements, such like the gold, is sort of the another mystery. And then, so the inside the neutron star is also the very interactive the mysteries. So there are so many mysteries exist to understand the universe of this. Then, this is a short summary of my talk up to here. So the early universe was dominated by elementary particles. The properties of elementary particles shape the current universe. Then, to investigating the properties of elementary particles, it means investigating the creation of the universe and its subsequent evolutions. So that means the elementary particle and the nuclear experiments can see the moment of the creation of the universe in various ways. Then, another question, to investigate the beginning of the universe, do you know how to do it? So there are some people said probably, so let's see the distant celestial objects or something. Okay, so seeing the distant object, such like the Hubble telescope or a James Webb telescope these days. However, so using the space telescopes, we can reach about the 400 million years after the birth of the universe. Okay, then another method is investigating the CMB, cosmic microwave background radiation. So that this is come from the very early stage of the universe. However, even investigating the CMB, we can reach approximately the 380,000 years after the birth of the universe. On the other hand, the imbalance between matter and antimatter is thought to have occurred before the 10 to the minus 10 seconds after the birth of the universe. So it means by observing the celestial events with using the space telescope or the CMB, we cannot reach the the era we really like to understand. Then, how to do? Let's imagine the Big Bang again. As I explained, Big Bang is a sort of the pure energy, and the matter and the antimatter was created from the Big Bang equally. Then the method is, let's make a mini Big Bang artificially. We have a technology to create the electron, which corresponding to the matters, and also the positron, which corresponding to the antimatters. And then we can accelerate the electron and the positron. And then also we can collide these electron and positron like this. Once the electron, the matter, and the positron, the antimatter collides, it creates the pure energies. And from these pure energies, we can create another matter and the antimatter. In our accelerator case, this is a sort of the quark, especially for the B quarks and also the anti-quark, anti-B quarks. So to make this mini Big Bang, we need the accelerators. I believe the accelerator will be reported by the professor later. And once this kind of the matter and antimatter or quark or anti-quark were created by the accelerator artificially, then the next step is how to detect this. Actually, but we already have the method to detect this kind of the matter and antimatter. So this is the typical particle detector which are being used in the Bell 2 experiment I belonging to. So the size of the particle detector is the 7-meter height and also the 7-meter long. So this is very big detectors. And also this is not the single detector. Actually, there are many different type of detector is the how to say the setup in the detectors. For example, the innermost detector is the silicon-based so-called the vertex detectors. And surrounding this, the vertex detector, we have the tracking detectors like this. And surrounding these tracking detectors, we have the different type of the particle identifier. So probably you think so that this is very big and complicated, the particle detectors. But the system of the particle detector is very simple. This is like a big digital camera. So there are triggers. So by making some mini big bang here, and with using this trigger, this is corresponding to the camera shutters. And then with using this trigger, we can take the snapshot of the detector outputs. Then finally, after these snapshots taken, we use the computing power to understand or to reconstruct the events, what happened in here. So this is the introduction of the introduction of this experiments we are doing at the KEK. But actually in KEK, not only for this kind of the experiment, but also the other experiments are ongoing. For example, the intensity frontier experiments. So the intensity, probably you do not have the intensity so far well, but the intensity, it means a sort of the statistics. So if the high intensity is corresponding to the high statistics experiments. So the BERI-2 experiment I am belonging to, I've already explained this kind of the things. Apart from the BERI-2 experiment, we have another experiment, so-called the kaon rare decay experiment. This kaon rare decay experiment is the exploring and also the measuring the process in which elementary particles called K mesons break symmetry at extremely rare rates and decay into special patterns and approach new physics. And also the neutrino experiment is exploring the origin of neutrino mass and the mechanism of oscillation by shooting neutrinos artificially generated at the high-intensity accelerator, so-called JPARC, toward a detector several hundred kilometers away. Here is the JPARC accelerators, and here is the Kamioka experiment site, where the neutrino detector is located. Not only for the intensity frontier experiment, we also have the another type of the experiment, so-called the energy frontier. Actually, the intensity frontier experiment is the investigate the effect of new physics that occur rarely due to quantum mechanical effects with unprecedented statistics. On the other hand, for the energy frontier is the create a mini Big Bang with unprecedentedly high energy state in an accelerator and search for unknown particles created there. There are two types of detectors we are using or we will use. One is the so-called the LHC, the accelerator. This is a proton-proton accelerator located in Europe, in France and Switzerland. So with using this, the very high energy accelerators, we can create the Higgs particles, and also we also expect some the supersymmetry particles and also some the mini black hole, etc., etc. And also the energy frontier research project at the International Linear Colliders are also ongoing. This is the electron-positron, the linear colliders. Anyway, so that these two different type of the large high energy accelerator experiments aim for the origin, reveal the origin of mass, supersymmetry, and extra dimensions, and so on. Another type of the experiment is the precision frontier.
5 minutes.
Okay. Precision frontier experiment. the precision frontier experiments pursuing new physics by measuring the rare decay and magnetic moments of muons with unprecedented ultra precisions. So I will not go in detail. There are two types of the experiments, muon rare decays and muon precision measurements. Plus, we have the nuclear physics frontier, exploring the mystery of a matter-dominated universe through experiments using ultra-cold neutrons and short-lived nuclei. So the neutron physics, nuclear physics research using strangeness, and nuclear physics research using short-lived nucleus. There are so many different types of the experiments are ongoing. And cosmic frontier, capturing the light of the early universe. It means the cosmic microwave background radiation and observing the state immediate after the birth of the universe. So we have planned to launch the satellites for that purpose in futures. So anyway, so that we have so many different types of the experiments or projects are ongoing, KK, IPNS. Because my talk is the first talk of the series of these seminars, so I would like to flash you the graduate slides of the graduate university for advanced studies. Actually, the KK is a part of this, the graduate university for advanced studies, so-called Sokendai. And inside KK, there are three sections. One of the section is the particle and nuclear section I am belonging to. So that if you like to know more detail, please click this link. Unfortunately, so that as far as checked yesterday, so the English page of the particle nuclear section has some problem, and for the moment it's not possible to accessible. But anyway, so you can get more detailed information from this link. Then, so inside the particle and nuclear physics, especially for the experimental group, as I explained so far, there are so many different types of the experiments are ongoing. The different of the color is the location of the experiments. For example, the blue parts mainly happen in the Tsukuba campus, and the yellow part mainly have the Tokai campus. This is another campus of the KK. And the gray experiments will be ongoing outside of Japan, for example, Europe, Chile, etc., etc. So this is my final slide, actually. So I would like to, emphasize the advantage of the belonging to the Department of Particle and Nuclear Physics, especially for the experiments. As you know, as you see, there are so many different or various types of the experiments. It means there are many choices of studies for students. And also, if you belong to the IPNS experiments, you can develop and use the state-of-the-art detectors by yourself. And also, you can perform the latest physical analysis, which may correspond or are related to the Nobel Prize directly. And also, there are so many large number of researchers to take care of students at the KK, IPNS. And the large number of research has a different backgrounds. It means the many experts in every field, not only for the detectors, but also the data acquisition, electronic system, software, computing. For example, my case, I'm the expert of the computing and software, actually. And also, it is a very rare opportunity for students to be involved from the beginning of the experiment, not only for the experiments currently in operation, but also the experiments that will start in futures. And finally, I would like to emphasize these parts so you can acquire world-class knowledge and experience as a researcher at KK, IPNS. So if you have some chance, please consider the IPNS KK for your future research careers. Okay, that's all. Thank you very much for listening.
Thank you very much, Hara-sensei, for your nice presentation. We'll have so many questions from our audience. So I think we will take the question in the end of last presentation from Hara-sensei, maybe later. So thank you very much, Sensei, for your presentation. Maybe we can start for the second presenter.
Sorry, before that, so that I have to
yeah.
apologize. Is it okay? So because I have another obligation, so that I have to leave this.
Okay, Sensei.
It's
Okay,
sorry
okay.
for this.
It's okay. And then if we have a question, then we can send from email.
Yes.
To
So
your, okay.
Yeah, my email address is written in the title page. So that
Okay,
if you have some question, please send the email to me directly.
Okay, thank you very much, Sensei. So we will send the question directly to your email later.
Yeah, thank you very much.
Sensei. So maybe we can start our second presenter. Would you mind, Aza, to present our second presenter CV? Then I can read it. Oh yeah, thank you very much. So our second presenter will be Professor Kazuhiro Mori Sensei. He is a professor at Institute of Material Structure Science, High Energy Accelerator Research Organization (KEK), Department of Material Structure Science, Sokendai. Education is Doctor of Science, graduate University of Advanced Studies, Sokendai. And research is material science, physical chemistry, and neutron diffraction with the diffractometer. And work experience is also belong to associate professor, research director, Institute of Kyoto University, and from 2002 until 2012. And then also before that, he also become a postdoctoral researcher in Institute of Material Structure Science and KEK at 2001. So he will speak regarding studies of battery materials using neutron scattering at GPark MLF. Please, Mori Sensei, you have time and your screen, and you have 30 minutes to do a presentation. Thank you very much.
Okay, thank you for introducing me. So can you hear me?
Yeah, we can hear you.
Okay, yes. I'd like to share my materials.
Please.
Okay. Is it okay?
It's okay. We can see you slide.
Okay. So thank you for again. And so today I'd like to talk about study of battery materials using neutron scattering at JPAC MLF. My name is Kazuhiro Mori from Institute of Material Structure Science, a high energy accelerator research organization. So wait a minute. Okay. So today's outline is here. First of all, I'd like to introduce basic properties of a neutron and basic theory of a neutron diffraction. And then let me show you some structural studies for battery materials. In the end, I'd like to summarize my talk. Okay. Yeah, so this map has already shown so this is a world map including Indonesia and Japan. If I remember correctly, so it takes about 18 hours by plane from the Indonesia to Japan. Yeah. As you come to Japan here, so you can find some neutron facilities like this. For example, Hokkaido University has Hokkudai Linak with neutron exploration source, and Kyoto University has KUR with neutron reactor source. In addition, JPAC MLF and so JRR3 are located at the Tokai area here, which is the largest neutron facility in Japan. Now I'm connecting so this Zoom online meeting from JPAC in Tokai here. Okay. As you can see, there is a building at the center of this photograph. Yes, this is JPAC MLF. JPAC MLF stands for Japan Proton Accelerator Research Complex Materials and Life Science Experimental Facility. So it has a variety of neutron spectrometers like this, which has been dedicated to structure and dynamic studies concerning physics, chemistry and material science. This photo shows a neutron diffractometer spiker, which is installed at the beam line 09. Here, this line. Okay, so I'd like to introduce this spectrometer in detail, so right there. Okay, so before talking about neutron diffraction, let us confirm what's neutron. Yes, you can imagine that neutrons exist within the nucleus. Okay. This is an atom which is consists of electrons and how to say nucleus, and so nucleus include protons and neutron. Yeah, so we use this neutron for our studies. Here is the basic property of a neutron. Neutron mass is 1.675 times 10 to minus 27 kilogram, and its charge is 0, and its spin is 1/2, which is something like very, very small magnet. So this slide showed how neutron beam generate. Now we have two types of processes. One thing, we can utilize the uranium fission reaction here. Neutron hit uranium nucleus, and then a couple of so neutrons are released as the fission reaction occurs like this. And so another thing, spiration is available to generate a neutron beam. In this case, protons are accelerated to near the speed of light in a very large accelerated, and then collide with heavy element like tungsten, mercury, so etc. Excitation occurs sooner. Finally, many neutrons are released along with other elementary particles. JPAC MLF has the spiration source, so like this. Okay, neutron is not only particle but also wave. It's well known as wave-particle duality, making it very essential to understand so neutron diffraction. The momentum and energy of a neutron can be described so like this, so here and so here. To understand diffraction phenomena, I want you to remember the wave on the surface of water here. Now, the wave comes from the left side, like this, and then collide with some post. At that time, you can see a ripple due to interference. The same phenomena occurs in atomic scale. This picture shows the arrangement of atoms in material. As you can see, neutron beam is scattered with each atom. So please note that neutron wave length is same as the distance between atoms here and here. If the Bragg's law, so 2D sine theta equal to lambda is satisfied, you can detect neutron on the detector like this as diffraction data. So collecting the diffraction data, and if you succeed to analyze the diffraction data, you can get information about the arrangement atoms in the materials. Okay. This slide shows the neutron diffractometer in JPAC MLF. Neutron beam generate regularly 40 milliseconds by spiration reaction. The generated neutron beam so from here reach to the sample here on the neutron diffractometer, and then the neutron scattered by the sample how to say okay, so are also detected on this neutron detector in the detector bank as a neutron diffraction data, so like this. Okay, so after collecting the neutron diffraction data, we try to determine the crystal structure or amorphous structure of material. This picture shows the neutron diffraction data for calcium dope cerium fluoride crystal, and this is Li2S, T2S5 glass, respectively. In the case of crystalline materials, lithobat method is very common to refine the crystal structure. On the other hand, reverse Monte Carlo modeling is very popular to visualize the three-dimensional structure for amorphous and liquid materials like this. So both methods are very interesting here. This slide shows the detail of neutron diffractometer spiker, which was designed and built by ourselves. It is located about 52 meters away from the neutron target. Yeah, here. The long flight path is essential to realize the high resolution on the diffraction data. The high resolution is about 0.09, so like this. In addition, high-grade elliptical supermillar guide tube has been installed to get the high intensity. So very long guide tube. So to get the high intensity. So here, yeah. So this is the overall so spiker, so neutron diffractometer spiker. Okay, let me move on to today's theme of battery materials. This picture shows the schematic illustration of lithium-ion battery, which consists of three parts: cathode and anode and the electrolyte. For example, in the cathode material, nickel and the manganese doped lithium cobalt oxide and spinel type lithium manganate oxide are so popular as cathode material. By the way, in general, burnable organic liquid are used in commercial batteries. So that's why there are big issues like leakage, ignition, etc. To avoid this, all solid state rechargeable battery have attracted much attention. Alternative to traditional lithium-ion batteries. Okay, so why do we use neutron for the battery materials? The answer is neutron can determine precisely atomic position for right elements like hydrogen and lithium and oxygen. This is because this light, so X-ray, so So in the case of the X-ray, so scattering amplitude is proportional to atomic number, but and it's a neutron scattering amplitude is independent of atomic number, as shown in this picture, so like this. In fact, as you can see here, for the lithium manganate oxide, which is positive electrode, so lithium and the oxygen are very clearly observed on the neutron diffraction compared to the X-ray diffraction. Yeah, so very beautiful picture. So we can get from this neutron diffraction experiment. Yeah. Okay, so this slide shows the operant neutron diffraction measurement. The deep penetration is also a big advantage of using neutron diffraction for batteries. It allows us to know the battery reaction very detailed inside the batteries. For example, this result provides the direct observation of changing structure for carbon anode material during the discharge process. As a result, the high current occurs in homogeneous lithium distribution in this anode material like this. So it's very useful to observe directly battery reaction by using the neutron diffraction or neutron scattering. Yeah, very beautiful, so powerful tool of the neutron diffraction. Okay, so nowadays, fluoride ion battery has received a lot of attention as the next generation rechargeable battery with high power density, a wide electrochemical potential window, and high reliability and long life span. In particular, the theoretical energy density of fluoride ion batteries are reached up to 5,000 watt-hour per liter, which is much higher than that of commercial lithium-ion batteries. Recently, we focused on lanthanum-doped barium fluoride, so electrolyte. So this is all solid-state the fluoride ion batteries. So it's a schematic illustration of it. Yeah. So why we focus on this material? Because its conductivity increases by 4 to 5 orders of magnitude, so drastically increased in the conductivity. So it's very, so interesting, also very surprising. That's why we wanted to know the structural origin using neutron diffraction on the source spike. Okay, so let me show you the result of the crystal structure analysis for barium lanthanum fluoride. This is the neutron diffraction data. The red mark indicates the observed data, and light blue solid line indicates the calculated data, and the blue solid line is the difference between observed and calculated data. As you can see, we could obtain excellent fit like this, and finally refine the crystal structure of this with what to say. Okay, so Okay, so anisotropic, so thermofracted, thermofracted. Okay, so the red sphere corresponds to the metal, and blue sphere is fluoride ion at the regular site of F1 site, and the orange ellipse correspond to fluoride ion at the interstitial site of F2. Now, I pointed out that the isotopic thermal factor of F2 was more pronounced toward the F1 site, so very widely expanded toward F1 of F2, so like this. And so if vacancies account for approximately 30% of the regular F1 site, so blue one, and so you can see there are so if vacancies are on the occupancy of F1, so here, yes. And furthermore, I tried to visualize the diffusion pathway of fluoride ion through the maximum entropy method, which is called MEM. The connected, so yellow area, so display the nuclear density. The connected area would carry the fluoride ion from one of the site to another. So that's why we conclude that fluoride ion migrate along the F1, F2, and F1 pathway. Fortunately, the findings of this study was reported in the Japanese press in 2020 here. Yeah, so I was very happy. Yeah. So next, so I'd like to introduce the collaboration with researchers coming from Indonesia. He is Dr. Pancha-san, who belongs to Research Center of Advanced Materials of BRIN. Actually, he stayed at Tokai until the end of July, so last month. His research subject, synthesis and structure study using neutron diffraction technique for the cathode materials, lithium nickel manganese oxide, with the addition of rare earth metals for lithium-ion batteries. Especially, he is very interested in using nickel on the cathode materials because he said Indonesia has largest nickel mineral resource in the world. So that's why he is so very interested in using the nickel on the cathode material. Yeah. So by the way, come to think of it, so this nicest Indonesia map is a present from him to me. Now I put nickel material, so it's very nice. Yeah. So thank you for sending me this one. Thank you, Pancha-san. Okay. He looks very interested. So first of all, sample preparation is done, and then setting up sample into the superhedral PD. So which is so another neutron powder diffractometer. And after that, we discuss showing the present data like this. And in addition, so I want to tell you that she is Dr. Nuiko Puji Ayu. We always call her Ayu-san, who is a new staff member of KEK. So she also helped a lot to his experiment like this. Yeah. Okay. Maybe time is coming. So I'd like to summarize my talk. In this presentation, I could show you some interesting topics using neutron diffraction. For example, studying about so battery materials for lithium-ion battery and so fluoride-ion batteries like this, as well as designing a neutron diffractometer. So it's a spiker. Finally, I'd like to send you some message to young people in Indonesia. If you come to KEK in Sokendai, I provide the three things. One thing, you can study about physics, physical chemistry, and some material science using neutron scattering. And you can design and make functional materials like battery materials by yourself. And how to say? So also, you can design and build special environment equipment or neutron diffractometers. For example, this is operance of battery cell for special neutron diffraction experiment. So there are some very interesting things in this Sokendai at KEK. Yes.
So,
well, wait a minute.
okay.
This is a final slide. Okay. Okay. We have already had a good relationship between Indonesia and Japan by Sokendai. So Pancha-san and Ayu-san and I are the Sokendai family. So we got doctoral degree from the Sokendai. So we are looking forward to working with you at the Sokendai in the near future. Okay. So thank you for your attention. Thank you very much.
Thank you very much for
Thank you, Mori Sensei.
I think Dr. Teguh is also attend this seminar. So thank you very much for your nice presentation regarding about neutron scattering, also the application of its technology. So I think we can open discussion later on if you have time, Sensei, after Honda Sensei presentation. Thank you very much for your nice presentation. Okay, thank you. So maybe we can continue to our third presenter from Yamamoto Sensei. Maybe Aza can show his CV. Okay, thank you very much. So our third presenter will be Professor Naoto Yamamoto. Yamamoto Sensei is associate professor at Accelerator Laboratory with High Energy Accelerator Research Organization (KEK) also, with education from PhD from Department of Science on Nagoya University, Nagoya, Japan, and his latest research about theory and design of RF accelerator structure and RF system for accelerators, particularly for higher harmonic RF systems. In his working experience, he works as an assistant professor, Accelerator Laboratory, High Energy Accelerator Research Organization (KEK), Accelerator physicist with radio frequency groups from 2015 and 2019. Before that, he also worked as assistant professor, Accelerator Division Nagoya University with Synchrotron Research Center and NUSRC from 2007 to 2015. So Yamamoto Sensei will talk about regarding about the studies of for future light source at KEK Proton Factory. So Yamamoto Sensei, you can start your presentation. Your time will be 30 minutes. Thank you very much.
Can you hear me?
Yeah, we can hear you and then we can see your slide.
Okay. So can I start?
Yeah, of course, you can start your presentation, Sensei.
Okay, thank you. Good morning. I'm Naoto Yamamoto. So I'd like to talk about studies for futurized sources at KEK Photon Factory. Okay. So before my main talk, I'd like to introduce our future plan briefly. So at present, we work for 2 future plans in different time scales. So one is a short plan, which is a Photon Factory upgrade. So since PF has been in operation for 40 years, then we are renovating and improving the equipment. So this is an upgrade project of existing accelerators. Another one is long-term plan, which is Photon Factory Superin 2030, after 2030. So this is a greenfield project, and a new ultimate synchrotron ring is expected. So there are many R&D subjects for graduate students and young researchers at KKPF. Okay, so this is the content of my talk. So today I'd like to talk about, at first I'd like to explain what is synchrotron light source, and then I will introduce KK Photon Factory, and future light source of KKPF is shown. And at last, I'd like to introduce some recent PhD themes on KKPF. So this picture is our facility, and we have 2 synchrotron rings at KEK Tsukuba campus. Okay, so in my talk, so for these 3 topics, I'd like to talk using this Photon Factory booklet. So this booklet consists of a cover page and 3 other pages. You can get it from the following link, and a brief introduction of synchrotron light sources and KKPF are shown here. So here, this is the first page of the booklet, and upper side of the page, we can see the roof and a roof of Photon Factory and injector tunnel. And focusing on this part, there is a nice introduction about synchrotron light sources. So here, so the section name is "What is synchrotron radiation?" And the explanation of synchrotron radiation is found. So in this paragraph, synchrotron radiation is electromagnetic waves emitted when electrons accelerated to nearly the speed of light undergo a magnetic field that changes their direction. And it covers a wide range of wavelengths from infrared to X-rays. So here, I'd like to explain more detail in next slide. So synchrotron radiation is a phenomenon introduced in electrodynamics and described in advanced electrodynamics textbook, such as Jackson's, for example. And synchrotron radiation, or light, is electromagnetic waves emitted by relativistic charged particles moving through magnetic fields. And synchrotron light source, or synchrotron accelerator, is an equipment to control such relativistic charged particles. So this left side figure shows the photon emission from electrons in the dipole magnet. So in usual, the electron is used as charged particles because its mass is very light and easy to generate and control. And the left side, right side figure shows the photon emission from magnetic arrays. So we call this type of magnet an undulator. So, a unique feature of synchrotron accelerator is their ability to produce very intense light over a wide wavelength range. Okay, and back to the booklet and move to the next paragraph. So, X-rays, soft X-rays, and vacuum ultraviolet, which are light with short wavelengths, can observe the nanoscale properties of materials, such as the atomic arrangement and the behavior of electrons in the materials. And synchrotron radiation is a bright light with highly directional property that enables precise and accurate measurement of small samples. Okay. And here there is some illustration and plot. And this plot shows how bright photon is emitted in each wavelength from some photon sources, so such as sunlight and X-ray tube and synchrotron accelerators. And here there are some illustration. This is observable samples corresponding to each photon energy. So if you use visible light or UV, you can observe cell, bacteria, and viruses. On the other hand, if you use soft X-ray or X-rays, so micromolecules or molecules can be investigated. So, and this plot shows brilliance. So this axis, brilliance as a function of photon energy, and as shown, by using synchrotron source, it is possible to get these light with performance that is not available in nature. Okay, and from now, I'd like to introduce the key parameters which characterize the performance of the synchrotron source through the understanding of wavelengths and brilliance. Okay, so at first, I'd like to start with wavelengths. So wavelengths means which wavelengths are obtained from a certain synchrotron source. In practical, this plot shows the brilliance spectra at KEK photon factory. And this blue and red curves shows available wavelengths from dipole and undulator magnet, respectively. And the available wavelengths can be expressed by a new parameter, critical energy. So that is shoulder position of this spectrum. The critical energy is given by this equation. And so from this equation, the critical energy is proportional to the square electron energy and proportional to the magnetic Can you hear me?
Yeah, we can hear you, Sensei.
So where can you see?
We can see. We cannot see your slide. I think you need to share again.
Okay.
Okay.
Okay. Can you see my?
We can see your slide. Yes.
And where can you hear?
Yeah, we can hear you. Yeah.
So can I start this slide?
Yeah, of course you can. You can start with the slide.
Okay. So the critical energy is given by this equation, and this energy is proportional to the square of electron energy and proportional to magnetic field strength. So sometimes the field strength is related to the circumference of the ring. So the electron accelerator energy and magnetic field strength are key parameters for knowing accelerator performance. And let's move to the brilliance. So the brilliance is expressed in this unit. So this photons means the number of photons. And here this part is the size of spread of photons. So number of photons is proportional to the electron number in the unit of coulomb or ampere. And size and spread of photon correspond to the electron distribution at emission point in phase space. And in accelerator field, the size and spread is evaluated using a quantity called emittance. So then to obtain the high brilliance, so increase of electron number and reduction of emittance becomes very important issues. So in summary, so in order to obtain very high brilliance photon beams at desired energy, so we are studying, researching, and considering how to control the large number of electrons precisely. So how to focus the electrons and keep them stable, and how to generate the special photon that cannot be obtained in nature. Okay, so let's move back to the booklet and go to second pages. So the detail of photon factory is shown here, and I'd like to talk about accelerators. So here is an overview of light source accelerator. So, and the accelerator consists of injector, magnet, and vacuum chambers, monitors, radio frequency cavities, andulators, and so on. So I'd like to explain these components one by one. So at first, injector. So in this figure, an injector is located here. So injector generate, accelerate, and transport electrons in the ring. And so there are many magnet and vacuum chambers and monitors is in the ring. And magnet controls the electron orbit in the ring, and vacuum chambers prevent the electron losses in the air and keep the electron for several hours. And by using monitors, we can measure the position, size, and charge of the electrons. And next is radio frequency cavities. So cavity accelerate and compensate the energy loss of the electron in the ring. So because the electron loses the energy by emitting the synchrotron radiation in the ring. And there are many insertion devices in the ring, and brilliant photons are emitted from the electrons. Okay. So next, so move back to the booklet again and go to this area. So here, so by using this slide, this part, I'd like to introduce KEK photon factory. So KEK has two synchrotron sources, and each source has various experimental stations for users, and the users can use the brightness photons at the same time. So this figure shows the beam line of the photon factory, And at present, there are 48 beam lines in our facilities. And so these are parameters of our storage rings. So first here, PF 2.5 GeV ring. So the energy of this ring is 2.5 GeV, and circumference is 190 meter, and beam emittance is 34 nanometer radian. And for the another ring, so PF advanced ring, so its beam energy is 6.5 GeV, and circumference is 380 meter, and the beam emittance is about 300 nanometer radian. So these rings were constructed about 1918s with cutting-edge technology of that time, but at present, these emittance are 1 or 2 order large compared with recent constructed facilities. And then I cannot say the performance of these rings are good enough. So recently we proposed a new facility. So here in the booklet of this area, so the detail of future source is shown. Okay. So recently, we proposed future light sources using the world's most advanced accelerator technology. So this is a schematic of our candidate of future light source. So this machine consists of a pulse superconducting liner and a storage ring called hybrid ring. So this hybrid ring is used as a storage ring, and at 10 Hz, super brilliance beam is coming from superconducting liner and pass through the hybrid ring. So this super brilliance beam is called single pass beam, shown in red color in this picture. So we believe this two photon beam having different color and size pioneer new research field. So this figure is the image of experimental station and samples. So at the experimental station, so two different photons coming from rings, and so in this figure, so there are large size photons from SR, and there are very small focusing light from single pass beams. So by using two different beams, the user can observe average information and very special image of some active area of the samples. Okay, and to realize this new light source, PF members and KEK staff are actively conducting research. Photon Factory Accelerator Group has many R&D subjects suitable for graduate student themes. Okay, at last, I'd like to introduce recent themes of graduate student. So in this physical year, students will receive their PhD for their work on synchrotron radiation accelerators. So one is the development of pulse multipole magnet for beam injection in light source by Yaoru. And another is the development of the 1.5 GHz TM020 type harmonic cavity for future synchrotron light sources by Takaaki Yamaguchi. So the first one is about pulse electromagnetic magnet and injection of straight rings. And Dr. Yoru developed a new pulse magnet after many complicated simulations and experimental studies. So this is an example. This is a magnet designed by Yoru, and this plot shows the temporal performance of this magnet. And another one is about radio frequency cavity of straight rings. So Dr. Takaaki Yamaguchi designed new RF cavities after many complicated simulations and experimental studies. So this is a picture of aluminum model of this new cavity. And this plot shows the calculation result of thermal and structure analysis of this cavity. Okay, that's all. Thank you very much.
Okay, thank you very much, Yamamoto-sensei. I think that we still have another 10 minutes actually, but it's okay. We can start our discussion later earlier. So thank you very much for our third presenter. So we already have 3 presentations regarding about several matter structure, particle physics, and also with the light source with the proton factory. So I think we have our last presenter is Honda Sensei. The CV he is the Dean of the School of High Energy Accelerator Science and graduate university for Advanced Studies, Sokendai. He also professor at Accelerator Laboratory with High Energy Accelerator Research Organization, KEK. His education is Doctor of Engineering, University of Tokyo. And his research is accelerator science, synchrotron radiation storage ring, and also vacuum science. And his working experience from 2020, he's a Deputy Dean, School of High Energy Accelerator Science, Sokendai. And 2016 is Chair of Departments Accelerator Science and School of High Energy Accelerator Science, Sokendai. And from 2009, is Associate Professor with Accelerator Laboratory, KEK, and also he's maybe the first work is 2005 with Associate Professor Institute Material Structure and Science in KEK. So we already have 3 presenters. So Honda Sensei will talk about guide for study in Japan, especially in KEK and then Sokendai. So Honda Sensei, please screen in time for you.
Thank you for your nice introduction. I will share my slide. Please wait.
Yeah.
Oh. Can you see my slides?
Yeah, we can see your slides, Sensei.
Okay, I will start my presentation. So, first of all, I would like to express my deepest gratitude to Dr. Awaludin, Dr. Rifai, Dr. Karina, and Dr. Emi, Dr. Pancha, Dr. Taufik, and all other involved at BRIN for giving us this opportunity today to introduce KEK and Sokendai to us young staff and students of BRIN. I hope that today's lecture will be useful information for all of you. So I will give you a brief description of KEK and Sokendai as a place where you can study abroad and can earn PhD. Oh, next slide. Oh, okay. Oh, 3 lecturers already show you detail of science, and KEK is a world-leading accelerator institute. We have world-class high-energy accelerators, Super KKB and JPAC, and synchrotron radiation facility. We called it Photon Factory, And we have two accelerator, PF-RIN and PFAR. And we have other small accelerators for developments. For example, accelerator test facility, superconducting RF test facility, and compact energy recovery LINAC. And another accelerator is medical application, IBNCT, Ibaraki boron neutron capture therapy. And we have two large campuses in Ibaraki Prefecture. One is the KEK Tsukuba campus. In Tsukuba campus, electron and positron accelerators in operation. The LINAC has a length of 600 meters, HGEB LINAC, world-class LINAC, and the injected by LINAC, we have a large 3-kilometer electron-positron collider, Super KKB, and Photon Factory has PF-RIN and PFAR. And we also have Tokai campus. We have here high-power proton accelerators in operation. LINAC, 3-jet synchrotron, and 30-jet synchrotron. And we have experimental facilities, neutrino beamline, and materials and life science facility, MLF, and hadron physics facility in Tokai campus. And 3 lecturers show you the science detail. I believe high energy accelerators are indispensable tools for exploring the world. Hara Sensei introduced mystery of the birth of the universe by explore the elementary particle physics. And Mori Sensei show you the neutron scattering material science region. And Yamamoto Sensei introduced to you the accelerator science, how to make or how to design accelerator itself. And he also operate the accelerator. And here I show you the structure of Sokendai and KEK. KEK has 2 institutes and 2 laboratories. One is the Institute of Particle and Nuclear Studies. Hara Sensei belongs to this institute. And Department of Particle and Nuclear Physics of Sokendai housed in this institute. And we also have another institute, Institute of Materials Structure Science. Mori Sensei belongs to this institute. And Department of Material Structure Science of Sokendai housed in this institute. And we have 2 laboratories, Accelerator Laboratory and Applied Research Laboratory for technical research laboratories, Applied Research Laboratory. And Department of Accelerator Science of Sokendai housed in these 2 laboratories. And I and Yamamoto Sensei belong to Accelerator Laboratory. And the doctoral training at KEK is carried out by the 3 departments of Sokendai. You can earn a PhD while conducting research at KEK as a Sokendai student. And what is a Sokendai? Sokendai is one of the national universities of Japan. It is a graduate university for advanced study. We call usually Sokendai, Japanese abbreviation. And it is a graduate university. And 5-year system doctoral course is the standard. And we also have 3-year doctoral course. And Departments are housed in inter-university research institutes of Japan. The inter-university research institutes are established for joint use by universities in Japan, and all institutes are large-scale world-leading research institutes, and 20 institutes in various research fields. Here is an example, placement of inter-university research institutes located throughout Japan. And among these institutes, KEK is the largest institute, and we have 3 departments of Sokendai. And I'll show you the related institute with KEK. We also have Department of Fusion Science in National Institute for Fusion Science, and Department of Molecular Science in Institute for Molecular Science, and in National Astronomical Observatory, we have Department of Astronomical Science, and Institute of Space and Astronautical Science, space rockets and artificial satellites, Department of Space and Astronautical Science. And we also have National Institute of Informatics, have Department of Informatics. And all these institute house Department of Sokendai, and 20 to 80 students study their doctoral research in this department. And KEK has the School of High Energy Accelerator Science and 3 departments. And in Department of Particle and Nuclear Physics, theory group and experimental group. And Department of Material Structure and Department of Accelerator Science we have. And the feature of Sokendai, we have high ratio of international students. In all Sokendai, about 30% student is international student. And in the School of High Energy Accelerator Science, in particle and nuclear physics, 22%, and material structure science, 42%, and accelerator science, about 50% is international students. So I will introduce how to enroll to Sokendai. First, important thing is consultation for enrollment. Please contact us with your CV. Feel free to contact the chair of the department in which you are interested. You can also contact the KEK Sokendai office by email. Then the chair of the department will introduce you to a potential supervisor and discuss your doctoral research topic and research plan with your potential supervisor. And we can invite you to KEK for a short trial period if you wish. Sokendai will pay your travel expenses, and please have experience the research facilities at KEK. And this is a selection procedures for international students. First, documentary screening based on the application form. But you don't worry, your prospective supervisor will guide you in the preparation of your application form. And GPA requirements and English test scores will be required to win a Japanese government scholarship. English language qualifications are recommended to be obtained in advance. And the main selection is interview via internet. You have no need to come to Japan for the entrance examination. And international students usually enroll in October. The usual time for submitting application and entrance examination is around December of the previous year of your enrollment. And for privately financed students, have the second round of application from April to May every year. So you can detail official information on admissions in Sokendai web page. Please search by Sokendai and admissions. You can see the information about how to apply to Japanese government scholarship and how to apply as a privately financed student. Privately financed students includes international applicants with foreign government scholarship. And official information, please contact Student Affairs section of Sokendai. And we show you the scholarships. It is important to cover life expenses in Japanese study, in study in Japan. The most useful scholarships is Japanese government scholarship, mixed scholarship. In all Sokendai, 44% international students obtain this scholarship, and in KEK, 70% students get this scholarship. This scholarship cover full support for tuition fees, living expenses, round-trip travel, etc. So using this scholarship, you can concentrate on your studies with peace of mind. And another chance, you can get scholarship from KEK. This is for the late 3-year doctoral program. But we have limited quotas because this is managed by donations from the public. And you add the salary of salary as research assistant of KEK to secure living expenses. And other students awarded by scholarships from the government of the student's home country. So the main scholarship, I show you the Japanese government scholarship, mixed scholarship. First application process is application to Sokendai. This is called University Recommendation course. We have regular quotas, 2 persons each year for all Sokendai. This is a limited person, but now the KEK's Sokendai departments have additional quotas in fiscal year 2024 and fiscal year 2025, more than one for each department. Mainly for students from Southeast Asia. So usually the enrollment period is October each year. Application and selection take place around December of the previous year. Now it is a good chance to win the next scholarship, I think. It is one note that this additional quotas program is only for the 5-year system course, but master's degree holders are welcome to apply to this additional quotas. And another note is the age limit at the time of application, 35 years old or younger. This is the age limit, please remember. And another process to get mixed scholarship is embassy recommendation process. Please apply to the Japanese embassy in Indonesia. And after passing the screening, please contact Sokendai for letter of acceptance. So Sokendai Sokendai will shift from the current 6-school system to the system of 20 programs under the one integrated school in April 2023, this April. And please remember one thing, the name of department is changed. We call department, but the name is changed to program. The Department of Accelerator Science, we call Accelerator Science Program, and Material Science Program, and Particle Nuclear Physics Program. Please remember when you check the home web page of Sokendai. So that's summary of my talk. KEK is please research in KEK for your doctoral thesis. And Sokendai trains doctoral students in KEK's excellent research environment. And KEK attracts the great attention of Asian students and welcomes international students. Now, our school has additional mission quotas for the next scholarship, so I think it is a good chance to study at KEK for Indonesian students. If you have interested in study at KEK, please feel free to contact us directly. We would like to expand our partnership with BRIN in the development of human resources. Thank you. Thank you for your attention.
Thank you very much, Honda Sensei, for your nice presentation. It's quite comprehensive and precise information regarding about how to study in KEK, especially in Sokendai. And also you explain about how many kind of scholarships that can our young researcher can be applied. So our Indonesian student can apply the scholarship and can study in KEK, especially in Sokendai. So we have maybe 10 minutes open discussion because our limited time. So I will open to audience, then can raise hand and then ask question to our presenters from. I'm sorry, Hara Sensei already leave the webinar. So we have Mori Sensei, Yamamoto Sensei, and Honda Sensei. So please raise hand and then tell your names and then where you're from, and then what kind of question you want to ask to the presenter. Please. We also have several researchers that graduate from Sokendai. Maybe Dr. Amy or Dr. Taufik can raise hand. Or
yes, Pak Rifai. Good afternoon, Honda Sensei. Thank you so much. I'm so happy to see you here. So I have a question to Yamamoto Sensei regarding the PF accelerator. In your presentation, you mentioned there are 2 plans for the PF, upgrade the existing PF, and also for the long term, KEK has a plan to make the new machine. And I think it is like an opportunity for a graduate student and also young researchers to join the R&D. For the graduate student, Honda Sensei already explained the procedure. Either it's a 5-year doctoral or 3 years doctoral. How about the young researchers? How is the procedure if, for example, BRIN want to send young researchers to involve in the project, and what is the target? I mean, how about the topic? Who decided the topic, and what topic that possibility for young researchers if they want to join in BF project? I think it's my question.
Okay, thank you. Thank you, Dr. Amy. So I think Sensei can answer directly, maybe.
So I think Honda-san
Oh, this is okay.
can answer, have some answer.
Okay, I will answer your question. I show you maybe the chair of department introduce you the potential supervisor, and please discuss with potential supervisor. But the first, what region you are interested in? It is an important thing. You are interested in accelerator science or particle and nuclear or material science. It is an important thing. And please contact the department you are interested in. And after we are contacted by students, we introduce a potential supervisor. And potential supervisor discuss with students how to make a plan, research plan for around PhD in 3 years or 5 years. And for example, in accelerator science, most students have not so many experience about accelerator science. In that case, we recommend the student if students have master degree, but we recommend 5-year course to newly study the accelerator science and to earn PhD in 5 years. We usually recommend 5-year course. And if you have experience in materials science or particle or nuclear physics, we recommend if the student has a master degree, we recommend 3-year course. And the potential supervisor will discuss the students about their doctoral research topic. I think this is a usual procedure how to make a research plan for doctoral thesis.
Okay, thank you, Sensei. How about the age? There is a age limitation. For example, as I know, for MEC scholarship, there is a age limitation, right? How about if the private, if we have a scholarship from Indonesia or others, is there also a age limitation to study either 5 years or 3 years doctoral?
It is depend on the period of scholarship. In your case, you have a 4-year scholarship from Indonesian government.
Yes,
in that case, we recommend a 3-year course. And in the period of scholarship, we have to approve the research for doctoral thesis, I think. And I show you the Japanese government scholarship, MEC scholarship. We have additional quotas for 5-year course now. But if you have master degree, maybe when you have a period of 5-year scholarship, but I think you can finish your doctoral research in 4 years, I think. Maybe 1 year shorter than the scholarship period. Maybe it is possible for you, I think.
Once more question. For Max, the student candidate, it should under 27 years old or
35 years old. Under 35 years old is the limit for a mixed scholarship.
Oh, okay. And once more question, Farifai, is it okay?
Okay, it's okay.
Okay. For a young researchers, for a graduate student, I think it's clear. How about the young researchers? For example, we have young researchers from BRIN. If we want to send some of them to KEK, for example, to involve, like Yamamoto Sensei said, in the upgrade of PF, I don't know, maybe in the part of the film lines or in other accelerator, is it possible, Sensei? And how is the procedure for that?
You mentioned about the accelerator upgrade plan and the research period, relationship, the accelerator upgrade plan.
Yes.
And,
yes.
It is a somewhat difficult program for the student for accelerator science. They research with large accelerator. Their research plan is depend on the accelerator operating schedule or accelerator improvement schedule. But usually the operating schedule is changed by budget or improvement plan is delayed depend on the budget. It is a very serious problem for students to research for improvement and or large accelerator operation. But we have to solve the difficult problem and
Honda Sensei.
Yes.
This is Kamitani. I felt that Emi-san is asking not about the case of a student, but young researcher as visit or stay at KK. Is it right?
So,
yes. Thank you.
So maybe the young researcher who have a PhD already and can append on the improvement project. Part of they maybe they research in part of the improvement program. It's no problem, I think.
Okay. So is it possible? Okay. Thank you so much, Honda Sensei, Kamitani Sensei. Thank you so much.
Thank you.
Okay, thank you very much for Honda Sensei and Kamitani Sensei. And maybe this one regarding about Fukuda Sensei talk before with us about regarding about the LINAC, I think LINAC projects. Okay. There's another. This is our last audience. Dr. Emi, can you shut your mute your? Okay, thank you. Maybe the last question, maybe from Mr. Oji.
Okay, thank you.
Okay.
Can you hear me?
Okay, of course we can hear you.
Okay, thank you very much. It's very interesting presentation. I have a question to Professor Kazuhiro Mori about what kind of topic or research in your laboratory for now, especially for the prospectus PhD student. And for the Professor Toharu, I think yes, a limitation. I just want to know about the limitation. I think it's the same question with Ms. Ami. But yeah, I think the limitation sometimes is not only in for scholarship, but also sometimes for the research laboratory also. Is there? I just want to know if there's no limitation age for the PhD who they want to continue to research in the KEK. Yeah, I think that's it. Thank you.
Yeah, so it depends on the situation, I think. Yeah. In my so in my opinion, so I recommend to enter the Sokendai earlier. Yeah, because the we provide suitable theme for the young people to enter the Sokendai. For example, so enter in the master course. Yeah. Yeah, so it's very difficult to answer the question. So I will ask with the personnel so about this. Yeah. Yeah. So Honda sensei. So how about the reputation of the entering the young person to the enter the Sokendai? I guess it depends on the situation. Is that correct?
Yeah.
Okay. So I think the age limitation will be 35 for the scholarship, but the laboratory is depend of
yes.
when you go there, I think, yes. So
okay, so feel free to contact me if there are anything so I can do for you. Yeah, so please send the email or something about this. Yeah.
Okay.
Thank you, Mori-sensei.
Thank you. Thank you.
You're welcome.
Thank you very much. So I think it's already 1 o'clock, more than 1:05. So I think the time is finished. So I would like to thank for all the presenters, Honda Sensei, Mori Sensei, Yamamoto Sensei, and Kamitani Sensei. Also Yamamoto Sensei, also Hara Sensei, that for your nice presentation. So I hope we will have a future more research collaboration and capacity building program in the future. So we hope we can send our researcher and young scientists, also our Indonesian student, to go study there in Sokendai, especially in maybe structural science, material structure, and also in particle physics. So I would like to thank audience that already attending our seminar. So we hope we can meet again in our Asoto Talks for next series. So thank you very much for your attending our seminar. Thank you, Sensei, for your coming.
Thank you very much.
Thank you very much.
Thank you.
Bye.
Thank you very much.
See you.
Thank you very much, Professor Takanori Hara, Professor Kazuhiro Mori, Professor Naoto Yamamoto, Professor Tohru Honda for the keynote speech, and thank you for Mr. Muhammad Rifai for being moderator. Ladies and gentlemen, Alhamdulillah, we have had a productive and inspiring time together. I hope you have found the presentation on this seminar are informative and helpful. On behalf of all the committee members, we would like to express my gratitude to all the participants and speakers for the participation today, and have a nice day. Thank you. Wassalamualaikum warahmatullahi wabarakatuh. See you on the next Accelerator Talk.
Honda Sensei, thank you very much. Yeah, arigatou gozaimashita.
Thank you so much, Honda Sensei.
Arigatou
Thank you so
gozaimashita.
much, Honda Sensei.